So it is my great pleasure to introduce a very good friend of mine, George Fuller. We have a tremendous entanglement, one might say, because I was the second to last graduate student of Willie Fowler's at Caltech, who won the Nobel Prize, and George was the last. And so we were contemporaries at Caltech together. We both worked on neutrinos for our theses. George never left neutrinos. I picked up photons. But now we're back on neutrinos with George and Evan, who you heard earlier in the summer, and I must say, having a great time with the topic. So George has done it all in the weak interaction sector, and he'll be describing aspects of that for you today.
Thank you, Dick. So I'm working in neutrino astrophysics, and you know, this used to be a really fun field to work in because nobody really knew anything about neutrinos. We knew they were light and they had weak interactions. That was about it. So it was wonderful. You could speculate about all kinds of properties they might have. And now the game has completely changed. Now it's hard work because there have been a lot of experimental measurements. So I just can't make up stuff about neutrinos anymore. I'll come back to something that's quite speculative at the end of this talk. But you know, Dick and I had a common advisor, Willie Fowler, who started out life as an experimentalist and who had great reverence for anything measured in a laboratory. And so we kind of have to pay attention now in astrophysics to the things that are measured about neutrinos. So I'll come back to that in a second. So the other measured things, we know what the baryon number is. Here I am at almost the home of cosmic microwave background physics. And we measure the CMB, with the ratio of the amplitude of the acoustic peaks. We have a very good handle on what the baryon number is, the number of baryons minus the number of antibaryons divided by the photon number. So, and we'll get that eventually to much better than 1% precision if I understand the forecast correctly. On similar lepton numbers, number of neutrinos, say electron-flavored neutrinos minus number of antineutrinos divided by the photon number, we have really very little to say about it. The best we can do is from astrophysics, actually. And the helium and deuterium abundances tell us that, and the measured neutrino mixing properties, which I'll describe, tell us that the lepton numbers, the analog of the baryon numbers, that reside in the neutrino seas have to be less than about 0.1. Kind of from a naturalness argument, you might think that they might be more like 10 to the minus 9, like the baryons. So the limits are not very good. And a lot of mischief can live under that so-called limit. Okay. And then another theme of what I'll talk about here is that compact object physics, binary neutron star mergers and stellar collapse, is exquisitely sensitive to lepton number violating processes and basically kind of funny neutrino flavor and spin physics that I'll describe. And the reason for this is that these objects are very well ordered. Their entropy is very low. The pressure that supports them against gravitation and dominates their dynamics is all coming from relativistically degenerate seas of electrons and neutrinos. And so if I change flavor, if I, for example, change an electron into something else, it gets absorbed on a proton, or if I change an electron neutrino into some other kind of neutrino, then that has immediate dynamical consequences in these objects. And so one of the reasons we're interested in both the early universe and compact objects is the synthesis of the elements. We think the lightest elements are synthesized in Big Bang nucleosynthesis, but heavier elements are synthesized in stars. So Willie spent much of his career working on the origin of the elements. One thing that Willie Fowler and Fred Hoyle and the Burbaches proposed in their famous 1957 paper, so it's almost 60 years old now, is this idea of the rapid neutron capture production of the heaviest elements like uranium. That remains a mystery as to where that occurs. We know it must occur somewhere, but we don't know where it occurs. So really what we would like to do is understand the role of neutrino flavor and spin physics and other kinds of neutrino physics issues in both compact objects and the early universe. And the early universe is becoming an interesting playground now. It's also quite not the wide open field it used to be, and that we know a lot now from the CMB, especially, about what happens at that epoch, and the prospects for learning more are very good. So stage 4 CMB polarization studies certainly will get the relativistic particle energy content at photon decoupling to higher accuracy. We'll get a straight up measurement of the primordial helium-4 independent of that relativistic degree, relativistic particle content. We'll get the baryon numbers I mentioned, even better. We'll get something called some M nu, which I'll talk about in a little bit. And with the advent of 30-meter class telescopes like the TMT, that the University of California and Caltech and Canada and China and India are in cahoots to build in Hawaii or someplace, and the GMT as well, there's a good prospect that we can get the primordial helium abundance to something of order 1 or 2%, which is interesting, and I'll show you how that's interesting. Evan actually talked about that. Moreover, in high energy astronomy, there's the prospect of X-ray telescopes that will have very high energy resolution. Hitomi is an example, and everybody know what happened to Hitomi? It's bad karma. We'll talk about that a little bit later. So in the whole nucleosynthesis business, in both the Big Bang and something like the R process associated with compact objects in some way, here are cartoons that basically summarize everything. So on the left is an early universe, and on the right is some kind of neutrino-heated outflow from some compact object environment, either the hot proto-neutron star left after a core collapse event, or perhaps the environment around a binary neutron star merger. So let's look at the early universe first. So let's just ride along with a co-moving volume element. And at very high temperature, always the ratio of neutrons to protons, which is a key thing in nucleosynthesis, is really set by the competition among the charge current weak interactions. So if I have a neutron sitting there, it can capture an electron neutrino and turn into a proton. And that proton can capture an anti-electron neutrino and flip back into a neutron. And that rate of flipping can be very fast compared to the expansion rate. And the basic physics of the early universe is that the expansion is desperately slow. It's driven by gravitation, which gravitation is the weakest force. And so things are slow. So even something as weak as the weak interaction can be fast compared to the expansion rate. So at high enough temperature scale, these are energy-dependent cross-sections involved in these captures. At high enough temperature, where the cross-sections are significant, these rates go fast compared to expansion, and they're roughly equal numbers of neutrons and protons. But as the temperature drops, absent any significant lepton number, remember on the previous slide, we don't really know what those lepton numbers are, but let's just say they're roughly 0. They're like the baryon number, close to 0. Then what would happen is this. The neutron's a little bit heavier than the proton, so that it's just energetically favorable to put the baryon number on the lightest particle, which is protons. And so eventually you wind up in a situation like this, which is mostly protons and a few neutrons. And then here's where the thermodynamics and nuclear physics comes into play. Both these environments are very high entropy. They're very disordered. So the entropy per baryon in units of Boltzmann's constant, we measure that. That's related to that baryon number we saw in the previous slide. So that's of order 10 to the 10. And in the compact object environments that we're thinking about for our process production, it's of order 100. Now, 10 to the 10 and 100 are basically the same on a nuclear physics scale. Okay? They're very disordered systems. And so what happens is the nuclear reactions all go like crazy in equilibrium because they're very temperature sensitive at high temperature. But as the temperature drops and the universe expands, those nuclear strong and electromagnetic interactions drop out of equilibrium. They become slow compared to the expansion. And so it's close to a freeze out from that equilibrium distribution. In the equilibrium distribution, the amount of any nucleus is a fight between terms, really. Disorder. You pay a price in putting a bunch of nucleons together in a nucleus on the one hand and binding energy on the other. And so when the entropy is high, the part of the nucleus that wins that competition is the lightest one with the biggest binding, alpha particles. So what happens is that as the temperature drops, you just aggressively take all the neutrons around, every nucleon you can get that will fit in an alpha particle, and you stick it in there. And so all the neutrons that are around get scoured out. And you're left with, at low temperature, a sea of mostly protons and a few alpha particles, and you're done. Because now the temperature is low and there are Coulomb barriers involved, and you really can't do anything else. So Big Bang nucleosynthesis makes alpha particles. That's it. Okay, one nucleon in 10 to the 5 winds up in a deuteron. So there's some contaminants here. And one in 10 to the 10 or 10 to the 9 or so winds up in a lithium-7 nucleus. But this is basically it. Okay? If I come over to this side, it's kind of the isospin mirror of what happens in Big Bang nucleosynthesis. So here you start off with lots of neutrons. It's a neutron star. And you're driving stuff off of this neutron star. So it starts out with a high neutron excess. And as it moves out, it's still being heated by neutrinos or shot through by fluxes of neutrinos. But now there's a twist. Since the neutrinos are coming out of the neutron star, the energies of these anti-electron neutrinos are higher than the energies of the neutrinos. The reason for that is the neutron star has neutrons, lots of neutrons in it. So this is an opacity source. The neutron star kind of lets go of those nu E's further out where it's cooler. That's the basic idea. So that in essence, the neutron excess in the neutron star is transmitted to the material that's being ejected by the neutrinos. And so this stuff remains neutron rich. And so it's the opposite of what Big Bang nucleosynthesis looks like. But nevertheless, the entropy is quite high, so that the nuclear physics part of this does the same sort of thing. And there's a freeze out from equilibrium in very disordered conditions. The entropy is a little bit lower, so you get more alpha particles. But now you isolate all the protons into alpha particles, and you're left with a sea of neutrons. Now the sea of neutrons, the neutrons have no Coulomb barriers. So this, by and by, produces uranium. So it's very interesting. If I change the neutron excess, these same pictures, this one makes helium, this one makes uranium. So this is all to get across the idea that the neutrino physics can be crucial in what you get out the other end in nucleosynthesis. Okay? So in the early universe, of course, Evan talked about this, so I'm not going to talk about it. Everyone around here knows about the CMB. What we'd really like to do is turn probes of the CMB into probes of the C nu B. And so there should be, if that picture of Big Bang nucleosynthesis I showed you is roughly right, and we have no reason to doubt that it isn't, we should get a comparable number of relic neutrinos as relic photons. And if I think about the number of neutrinos inside the causal horizon now, it's a rather large number. And even if neutrinos are extremely light, if I multiply that extremely small mass by that number, it could be dynamically important. And that can show up in interesting ways in fingerprints in the CMB and in the growth of structure, for example. So this is where we're trying to go with this. So I'm here with Evan and working with Dick and Joel, trying to turn probes of the CMB into a probe of the C nu B. So Evan talked a lot about the physics of what happens in weak decoupling in the early universe, and so I won't do that. He has a beautiful calculation in this picture that you've seen on what happens following the neutrino physics in detail through the epoch of weak decoupling and weak freeze-out, and the prospects for what we can do with stage 4 CMB are impressive, and we'll come back to that in a little bit. But let me now turn to, since you know about the early universe, we'll come back to the early universe, but let me talk about compact objects a little bit. So core collapse supernovae. Actually, it's neutrino emission. These are core collapse supernovae have progenitors that are massive stars, more than 10 times the mass of the sun. They evolved to the end point of their evolution in millions of years. Along the way, through a succession of hydrostatic burning phases, basically from core carbon-oxygen burning onward, the neutrino luminosity exceeds the photon luminosity. And so these massive stars are effectively giant refrigerators because of the weak interaction. So the entropy becomes very low in the center, in the core. And entropies of order 1 unit of Boltzmann's constant per baryon, not 10 to the 10 or even 100. And that's very cold. That's lower than the entropy of the air in this room by quite a bit. So it's thermodynamically cold, but the temperature is quite high, actually. It's more like 1,000,000 electron volts. Nevertheless, the neutrino emission sets, and this lowering of entropy sets the star up for disaster because the star is supported by relativistically degenerate electrons. Whenever you have a situation where the pressure support for some gravitationally bound system is that pressure support is supplied by particles or things moving at the speed of light, it's inherently unstable in general relativity. And there are a number of things that cause this iron core, the endpoint of evolution. So this is of order of the mass of the sun. It's of order the size of the Earth. And when it goes unstable through a variety of means, in about 1 second, it collapses down to a hot protoneutron star, initially with a radius of about 40, 50 kilometers. But within a second or two, it's down to about 10 kilometers in size. And if I look at the energetics of that, essentially all that gravitational binding energy is released as, or 99% of it, is really pumped into seas of neutrinos, most of which are trapped by the infalling material and by the high densities in the core. So where you might get excited about the optical display of a core collapse supernova, actually kind of puny compared to type 1As in terms of photons. But that's 10 to the 51 ergs, and that's 1% of the total gravitational binding energy released. That is 1% of the neutrino energy, which is roughly 10% of the star's rest mass. Okay? So that's the gravitational binding energy. The only other time scale that's really relevant here is the neutrino diffusion time. So this star collapses. It traps those neutrinos in. The neutrinos can random walk their way out, and that takes seconds. And when the neutrinos get to the edge of the neutron star, which we call, in kind of a misleading terminology, the neutrino sphere. The idea is kind of like the chromosphere of the sun, but this is actually quite different. It's more or less the fact that the density falls off very rapidly near the edge of a cold neutron star. In fact, with these hot neutron stars, right after the collapse, this neutrino sphere is a rather puffy thing, extended thing. In any case, you can imagine the neutrinos now free streaming coherently through an envelope of material on top. And we don't really care where the explosion comes from. We're not interested in that. So there's rough kind of equipartition of energy among all 6 different flavors. This is Dick Bond's PhD thesis. And roughly then I'm dissipating all that gravitational binding energy among those 6 species in a time scale of order seconds. And so we've got luminosities for each of the 6 kinds of neutrinos that's of order 10 to 51 or 10 to 52 ergs per second. So a prodigious flux of neutrinos. And more or less the same story for compact object mergers. The binding energy is mostly radiated as neutrinos for, say, binary neutron star mergers in spiral. Now, the arithmetic on the R process is interesting. So if we go back and look at the old papers from the 1950s and 60s by Willy and his collaborators and Seuss and Urey, we know that the mass fraction of baryons in the galaxy in our process material, like uranium and iodine and gold, is about 1 part in 10 to the 7. So that means with 10 to the 11 baryons in the galaxy, that means there should be 10,000 solar masses worth of the R process in the galaxy. The age of the galaxy is 10 to the 10 years, roughly. So the core collapse supernova rate is about once per century per galaxy like the Milky Way. So 100 million supernovae in the history of the galaxy. And we need 10 to the minus 4 solar masses of our process material per supernova to explain all that. That number is easy to get, and it's just about the right number we'd expect for stuff driven off from core collapse supernovae. There's only one problem. I've spent a number of years now working on putting the neutrino physics in to this model of where we get the R process. And when I put in standard model neutrino physics, we can show that this pretty much can't happen. Okay? It's very difficult to get the R process when I put in all of the neutrino physics. Okay, by contrast now, the most popular model for the origin of the R process is binary neutron star mergers. We know about a half a dozen of these things from binary pulsars in the galaxy. So this is astronomy, so 6 is easy. That's good statistics. So we back out a rate of about once per merger of once per 100,000 years per Milky Way equivalent galaxy. And in fact, the merger rate might be in this range of about 3 orders of magnitude. So this would, using the same arithmetic, this would be the same, the number of neutron star mergers. So if I, again, try to make all the R process with this, with a very high merger rate, I would need about 0.1% of a solar mass per merger to make all the R process. And at the lowest merger rate, I would need to turn the entire compact object and eject all of that as R process material, which is obviously a no-go. So if I get the best merger rate I can get, which is like 10 to the minus 5 per year per Milky Way equivalent galaxy, that gives me 10 to the 5 mergers, and I need something like 1/10 of a solar mass of R process material per merger. Now, the best numerical models now seem to suggest that that's tough to get. We might need more like, those models tend to suggest that you get something of order a 1%. I'm sorry, 1% of a solar mass and not 10% of a solar mass. So we don't know what's really going on there. And there may be, and these are, even the most sophisticated models now are fairly sketchy when it comes, there are many issues in physics that are not in these calculations. So the basic physics problem is that you're ejecting material from deep in a gravitational potential well, around a neutron star where the metric deviations are 10 or 20%. So that means the binding energies are something like 10 or 20% of the rest mass of a nucleon. And we got to eject this nucleon out of this potential well. So if I use intense neutrino fluxes to do that, think about that. The average energies of neutrinos in these compact objects are like 10 MeV. So if I have to supply the neutrino energy, the requisite neutrino energy to eject this thing from the potential well, each nucleon would have to interact, in a sense, about 10 times. So I need huge fluxes of neutrinos to do that. But then I just showed you how, if I have huge fluxes of neutrinos, they will reset the neutron to proton ratio. And if those energies are 10 MeV, the difference in mass between a neutron and proton is only over order 1 MeV. So what happens is that I have this beautiful hunk of pure neutron matter, which would make a wonderful R process. And then if I rely on neutrino energy to eject it out of this potential well, the neutrinos are going to change it to roughly 50-50, neutrons and protons. That's not necessarily very good for the R process. Okay, those processes. Okay, so you might say, great, don't use neutrinos to eject it from the potential well, and that may be the answer. Maybe there's some electromagnetic mechanism or some other astrophysical mechanism to rip this hunk of pure neutron matter out so fast that the neutrinos can't get a purchase on it and ruin the neutron excess. So that's, in a nutshell, the problem we're facing in the origin of these things. By the way, a key objective of advanced LIGO is to measure the neutron star merger rate. To really get a handle on that, we're going to have to wait till it gets its ultimate design sensitivity in 3 or 4 years. But that will be nice, because at that point, it will have a reach of something like 200 megaparsecs. And if you do the arithmetic, for some of those merger rates I saw, that would give something between an event a week and an event a year. So that'll be a measurable number. And so if the event rate isn't very high, we're kind of dead. And we're going to have to find a way to make neutron star, or rather I should say, either make the neutron star merger environment work or make the core collapse supernova environment work. And that may call into question, in my opinion, basic things in neutrino physics. So let's just go back. Yes? Yes?
Before you go on, when you're pulling out the material from a binary neutron star merger, is that sufficient to get it away from the merged object and reduce those fluxes?
Well, it doesn't do any good if the wonderful R process winds up in a black hole. That's true. So yeah, you've got to completely eject it.
I mean, you were saying that the high neutrino fluxes can perhaps reset the neutron to proton
Yes.
ratio. If you fling the material outward
fast enough, that won't happen. That's right. You'll decouple the neutrinos. That's my point.
Be kinematic from the merger.
That's right. So I could envision something like an electromagnetic ejection process. The magnetic fields in these binary neutron star mergers are immense. So that's not crazy. It's just maybe not in most of the models now. Okay?
Is there some sort of, you lose something though if you fling it out really quickly? Like you need a certain amount of time for these nuclear reactions to occur.
No. So no. In fact, this was Brad Meyer's PhD thesis. Brad Meyer is at Clemson, and Brad Meyer was Dave Schramm's graduate student in Chicago a while ago. And so his thesis was, what happens if I take a hunk of neutron matter at nuclear density and I just let it go? It disassembles, it heats up, it makes a wonderful R process. So that's what we'd be looking at. If I could rip that stuff out fast enough so the neutrinos can't destroy the neutron excess.
How fast is fast?
Well, okay, that's a very good question. So the answer to that is fast enough that it's faster than the typical weak interaction rates, the neutrino capture rates on neutrons and protons. Okay? And I can figure out, so that gives me a bound on how big the luminosities can be, neutrinos, because obviously the higher the luminosity, the rates are going to go like a flux times a cross section. So the luminosity divided by the distance squared is something like the flux. And I multiply that by the cross section, which is going like the square of the neutrino energy. So I have something to play with there. So luminosity times cross section divided by radius squared is what I have to compare to the actual material expansion rate. So I'd like the material expansion rate to be much faster than that. Or equivalently, the weak interaction time scale to be very long compared to the expansion time scale.
So how sophisticated are these calculations now? Because it's a highly asymmetric situation.
That's correct.
So for the transport of the neutrinos, that could really build some amusing asymmetry in it.
That's correct. So let me describe what I regard as the most sophisticated calculation, the best calculation now, which is, I believe, Radice et al. Just published in I think, April or May of this year. And in that calculation, there's rather sophisticated neutrino physics, Boltzmann neutrino transport kind of physics, but the neutrinos are spherically symmetric. The matter is not. Okay, so it's a 2D, GR code with a decent equation of state, I believe, but the neutrinos are spherically symmetric, and none of these neutrino issues I'm talking about are in there.
So with the flux limited diffusion, is that something like
I think it may. No, I don't think it's that sophisticated. No, I don't think so. I may be wrong about that.
Okay, so
I mean, if you think about it, you're right. I mean,
find an answer, but there's a lot of scope for
yes,
thinking about the neutrino
absolutely.
interaction asymmetries, which might allow you to get the neutron-rich stuff out.
Absolutely. But right now, we're not there. I mean, you're pushing the envelope of what you can do computationally because of, as you say, these are multi-spatial dimension calculations. Yeah. Okay, so this is just a quick overview of what we know about neutrinos and what we don't know. We have measured the differences of the squares of the neutrino mass eigenvalues, like this. And we just call those, there are 3 neutrinos, so there are 2 mass squared differences, the so-called solar scale and the atmospheric scale, and there you see them. We do not know the absolute masses of neutrinos, and we don't know the neutrino mass hierarchy. In fact, we don't even know the ordering of these 2 neutrino mass squared splitting. So we don't know whether we have the normal mass hierarchy. I don't know why this is normal, but where the solar scale's on the bottom and the atmospheric scale's on the top. And these are color-coded to show you how the flavors mix in there. I'll get to that in a second. And we can't, so terrestrial experiments, oscillation experiments, can't tell the difference between that and the so-called inverted mass hierarchy, where the solar doublet is on top. And then, so we can't even do that. Now, of course, what I'm about to show you is that we know that, for example, some M nu in cosmology is quite sensitive, actually, to whether nature has chosen the normal or inverted mass hierarchy for the ordering of neutrino masses. Compact object physics is very sensitive to which of these hierarchies nature has chosen. So the good thing is there are a number of experiments ongoing right now, and when I took some bets at the KITP last year in their neutrino program with experimentalists about when this would be measured, the answer I got was we will certainly know the mass hierarchy within 5 years. I don't know whether that's true, but it sounds good. And if we actually did know the neutrino mass hierarchy, then both the CMB connection with neutrinos and these kinds of neutrino physics connections with compact object physics become a lot more definitive. They make the astrophysics a much better probe of some of these unknown physics issues if we already know what this mass hierarchy is. So the main takeaway message from all the experiments that have been done over the last 20 years with neutrino physics is that the neutrino mass or energy eigenstates, which I'll call nu1 and nu2, are not coincident. They're not the same as the weak interaction eigenstates, the flavor states that tell how neutrinos interact with matter. Okay? And so there's a unitary transformation between those guys. And so I could write it like that. And it's conventional to write that unitary transformation between these two different bases as a product of rotations among the neutrinos. And we call that the Pmns matrix with those names associated with it. Interestingly, you can see here there are 4 parameters in this relationship, 3 angles and a phase, so-called CP violating phase or Dirac phase. And interestingly enough, physics is an experimental science. And these mixing angles are measured. And so we know that. In fact, theta 1,3 was a key one because it really says how electron neutrinos are coupled into mu and tau neutrinos in astrophysics in an important way. That was unknown until less than 5 years ago. And so now it's one of the best known measured things in particle physics, actually. So it's pretty good, at least in neutrino physics. We don't know the CP violating phase. And notice that it's called the CP violating phase for this reason. If I look at that relationship between the flavor states and the energy states or the mass states, and I take the conjugate transpose of that, so that would give me the relationship between the anti-neutrino flavor states and the same mass states. Okay? And notice what happens if I take the conjugate transpose of this, then the signs of these guys change. So what does that tell you? It tells you that if that delta, that Dirac phase, is non-zero, it says that the antineutrinos couple to the mass basis differently than the neutrinos do. So that means in some sense that neutrinos and antineutrinos would behave differently in vacuum. This is all in vacuum. Okay? That's where we measure things. Okay. One other piece of information. We don't know whether neutrinos are Majorana or Dirac. I'll come back to that in a second. If they're Majorana neutrinos, then there are additional CP violating phases that come into play. These are the so-called Majorana phases. You know, the only way we know how to probe those phases right now is in neutrinoless double beta decay, which I won't get into very much anyway. Possibly there's a connection with supernovae, which I'll tell you about. So what about the absolute masses themselves? I think, just writing this down, I think there are 4 ways that we can get at absolute neutrino mass. And you have to be very careful about that word neutrino mass, because in no case do we ever measure the neutrino mass. Okay? So here's the flagship, which is tritium beta decay. So a neutron in tritium turns into a proton, and beta decay, out comes an electron and a nu E bar. And we measure the electron spectrum. We can look at the endpoint of that spectrum. And what you're really measuring there from the shape of that spectrum, that electron spectrum, is the projection of the neutrino mass eigenvalues onto neutrino flavor. So effectively, the measure you have here is a Pmns matrix element squared weighted sum of the neutrino mass eigenvalues. And with the Catron experiment, we can probably get to about 0.2 electron volts. That's the design target for Catron. For a number of novel radio frequency experiments where you actually look at the cyclotron lines in electrons from beta decay, from tritium beta decay in a magnetic field. Project 8 is the main experiment there. At least a factor of 2 better if you can get this thing to work, and maybe even better, maybe even competitive with the CMB bounds at some point in the distant future if we can get these things to work. What about CMB? Cosmology. Effectively, what you're looking at here is something like the collisionless damping scale, how far neutrinos move in a Hubble time. And so what's usually called sum m nu is in effect a kind of weighted, kind of a relic spectrum, energy spectrum weighted sum of neutrino masses in the conventional sense. And so if you look at CMB sensitivity, I say here 10 millivolts. The science book, it says 15 millivolts, but I'm a theorist, so I think it's 10 millivolts. There you go. Another way to do this is to use spin flip, which I'll talk about in a second. Changing a neutrino into an antineutrino. That's what has to happen for two neutrons to change into two protons in a nucleus without emission of any neutrinos. So this provides, if you could measure this, this provides a constraint or a measurement of a coherent weighted sum of mass eigenvalues. So it's actually the Pmns matrix elements themselves, not the absolute squares of them, that weight the neutrino mass eigenvalues. And with sort of ton scale double beta decay experiment sensitivity that's envisioned, maybe something like 10 millivolts. So if we saw a signal, for example, and we knew it was a normal mass hierarchy, that would tell you that the lightest neutrino mass eigenvalue was something in excess of about 10 millivolts, which is interesting. Okay. All right, so neutrino rest mass brings up many issues which impact cosmology and compact object physics. Moreover, neutrinos are funny things. They're neutral particles, so they likely acquire mass differently than charged particles. And that's interesting. And then there are all kinds of theories about how neutrinos do acquire mass. So one outstanding question about massive neutrinos is whether they're Majorana or Dirac. I'll come back to that in a second, in a few slides. If Majorana, what are the Majorana phases? Obviously, that's it I just talked about. What is the Dirac CP violating phase? This may impact leptogenesis models and baryogenesis models, for example. Why are neutrinos so light? Why are their masses perhaps of order 0.1 electron volts, and in the same family of elementary particles, the quarks have masses of millions of electron volts, current masses? So that's an anomaly. And there's been an old idea in particle physics that seesaw-like schemes are the answer to that question. So we'll come back to that in a minute. But first, do this Gedanken experiment. Let's say neutrinos have a handedness, they're spin-and-a-half particles. So the weak interaction only sees left-handed neutrinos and right-handed antineutrinos. So in fact, the neutrino, like an electron neutrino, would have a spin pointed effectively opposite to its propagation direction. It's a left-handed particle. So do this Gedanken experiment. So let's say I take tweezers and I crank the spin around. And I can do that actually if there's a non-zero rest mass. I crank the spin around and force it to point along the propagation direction. Now that's an electron neutrino that's right-handed. So ask yourself this question. Is that identical to the antineutrino? I mean, antineutrinos are right-handed, the ones that interact with the weak interaction. So if the answer is yes, it's identical to the anti-electron neutrino, then we call that thing a Majorana neutrino. If the answer is no, it's some right-handed neutrino and the weak interaction doesn't see it, then we call that a Dirac neutrino. Okay? So if you study the Dirac equation in school, you know that if I have an electron, for example, because the rest mass is non-zero, there's always an amplitude to flip the spin to point in either direction, and that amplitude always goes like mass divided by energy. So same thing applies for neutrinos that have rest mass. But now the rest masses are tiny, maybe 0.1 electron volts or lower, and these energies that I just told you about in compact objects are like 10 million electron volts. So this number is very small. This is like, you know, the amplitude on the face of it is like 10 to the minus 7 or so, or 10 to the minus 8. So that's really small. So one thing we've discovered in our research recently on the theoretical side of things that's kind of surprising is that there's a way to coherently, adiabatically transform a neutrino spin from left-handed to right-handed. And as I just showed you, that's potentially very interesting because nucleosynthesis, for example, is very sensitive to whether we have new E's or new E bars in the mix. Okay. So why are neutrinos so light? This is the seesaw model. This is my version of an old slide by Boris Kaiser, one of the great experts in particle physics theory, experts on neutrinos in particle physics theory. So the idea is this. You start with some primitive Dirac neutrino. So there are 4 states for a Dirac neutrino. A left-handed active neutrino, a right-handed thing that's not an active neutrino, an active right-handed antineutrino, and a left-handed version of that that's not active. And so the idea is you join together the 2 active states into a Majorana pair and call that an active Majorana pair, and you join the 2 so-called sterile states together and say they form a Majorana pair as well. And then you posit or argue that the mass scales associated with these pairs, the product of them, is some really big mass scale squared. That's the idea of the seesaw. And then here's what we do. And this is an idea by Gelman, Ramon, and Slansky, and by Ravi Mohapatra and his collaborators. So the idea is this. I can kill 2 birds with 1 stone. I make the sterile neutrinos really, really heavy. And this product is fixed. So that forces the mass scale of the actives really, really low. So what have you done? You've explained why the active neutrinos are so light, and you've taken the sterile neutrinos, which are kind of an embarrassing byproduct of a non-zero neutrino rest mass, and you force them up to some really, really high energy scale where they won't mess up your experiments or won't mess up anything in astrophysics. Okay? So that's the basic idea of the seesaw model. Of course, all of this comes from the guy who thought of everything first when it comes to neutrino oscillations and neutrino physics, Bruno Pontecorvo, who was one of Enrico Fermi's students. He was the first to recognize that the handedness of the weak interaction meant that non-zero neutrino rest mass could enable neutrino spin flip from active left-handed states to sterile right-handed states. In fact, he did this before he came up with the idea of neutrino flavor oscillations. And of course, the takeaway message from neutrino experiments is that neutrinos do have non-zero rest masses. And this fact begs the question that was posed originally by Pontecorvo. Are there sterile neutrino states? And so let's just pretend that there are 2 kinds of neutrinos, an active electron flavor neutrino and a sterile neutrino. It's a flavor. It says that if your neutrino is exactly this flavor, it's an eigenstate of flavor, and it's sterile, that it has no interactions. Okay? The weak interaction just simply doesn't see it. And if I have only 2 neutrinos, and in that unitary transformation between them, there's only 1 parameter, we'll call it some kind of effective vacuum mixing angle. If this is true, which is what Pontecorvo suggested, then active neutrinos, if sterile neutrinos mix in vacuum with active neutrinos, they aren't really sterile. So, and a sterile neutrino could be propagating along, but it's mixing with an active. So, every once in a while it turns into an active species for a very short duration, right? And that gives it a handle, and we can see it. So, whereas active neutrinos would have cross-sections, typical standard model cross-sections, go like the Fermi constant of the weak interaction squared, energy squared. The sterile neutrino wouldn't really be sterile. It would have a cross-section that would go like this, down by sine squared of this angle. Okay? So now this begs a number of interesting questions, and you can ask whether these sterile neutrinos show up in nature anywhere. There are lots of constraints on them which I don't have time to talk about. I just want to finish with one speculative possibility, which is that if there's a mass, these things have masses associated with them also. There's a mass eigenvalue associated with nu1 and nu2. Let's say nu1 is the usual kind of active neutrino mass scale, 1/10 of an electron volt or lower. And this one is kilo-electron volts. You might say, wait a minute. That's not the unification scale we needed in the seesaw model. It's true, but there are so many variations of that that you might be able to accommodate a neutrino like that. So let's just say, so it doesn't wreck anything, let's just say that, it's got a mass of order keVs, but that mixing angle is 1 part in 10 to the 10, or 10 to the 11, or 10 to the 12. then it won't show up. And you can see that the cross-section will effectively be, the effective coupling will be 10 or 11 or 12 orders of magnitude lower than the weak interaction. Okay? Now, Planck and CMB experiments do not eliminate sterile neutrinos like that. And the reason for that is that if there were sterile neutrinos with the properties I just described, they would not have relic energy spectra that were anything like the active neutrinos. Their relic densities would be quite low, in fact. Okay? All right, and so there are lots of constraints we can put on sterile neutrinos. I don't want to talk about this. I didn't mean to show that. And so by and by, what I want to do, I don't know what I did to my slide here, is show you that if I can turn to the dark matter problem, so we have perfectly good dark matter candidates. Why introduce another one? Well, why not? We know from the CMB and large-scale structure and a number of sources that we live in an essentially critical closure density universe. But that symmetry, omega 1 is always 1, so long as we don't break the symmetry of homogeneity and isotropy. And that symmetry is a space-time symmetry. It's not a particle physics symmetry. It's basically agnostic as to what makes up the closure density. Now, we can constrain from astrophysical arguments what makes up the closure density. But nevertheless, there's room for all kinds of different things contributing to that closure density. In fact, we already know there are a bunch of different things contributing to it. So if I go with Pontecorvo's idea that there are sterile neutrino states, then it was a great idea that Scott Dodelson and Lawrence Woodrow had a little more than 22 years ago. And they pointed out something really interesting. If I do nothing else, just a quantum mechanical limit, just assume that active neutrinos and sterile neutrinos mix in vacuum with some tiny mixing angle, then every time an active neutrino scatters, that scattering is like a measurement. And if that active neutrino is a coherent superposition of an active and a sterile, and a scattering event is something like asking a question in quantum mechanics, are you active or are you sterile? What happens? You collapse the wave function, and every once in a while, like sine squared theta of the time, it'll collapse into a sterile neutrino. So you can start off with no sterile neutrinos, which is actually a reasonable approximation with only standard model physics and only that Pontecorvo coupling. And then what's Dodelson and Woodrow pointed out is that if you ask that the resulting relic density built up by all the scattering processes in the history of the universe is roughly the density you'd need for closure, that picks out a keV rest mass scale and very small mixing angles. And Shangdong Shi and I had a kind of variant of that where we matter enhanced that process with a tiny lepton number, which is nevertheless large compared to the baryon number. And that kind of can do the same thing, but then extend the mass range to tens of order 10 keV or higher, and producing a colder relic energy spectrum. And the idea is basically something like this. At very high temperature scale, lots of scatterings along the lines of what I just talked about mean that you can't produce many sterile neutrinos. The reason for that is that it's the quantum Zeno effect. If I set something to be active and then I start it propagating coherently, and I measure it quickly again, I force it back into its original state, and it has no time to build up phase to become a sterile neutrino. So at very high temperature in the early universe, the quantum Zeno effect basically demands that you not produce any, or dictates that you not produce any sterile neutrinos. And at relatively low temperature, the scattering rate falls off. So there's some kind of characteristic peak where most of the sterile neutrinos would be made. And they're made in very non-thermal patterns. So here's what a thermal relic neutrino energy spectrum would look like. If we do these calculations, here's what a sterile neutrino relic spectrum would look like. So, and there are other ways to make these things with dilution, for example, or whatever. So let me just cut to the chase and end with something on dark matter. If I can find this slide down here somewhere. So the characteristics of these sterile neutrino dark matter candidates are kind of interesting. They could be warmish and smear out small-scale structure, or they could be deadly cold, like heavy WIMPs, for example. Recently, James Bullock and Michael Boylan-Kolchin and collaborators have done kind of a calculation following the actual energy spectra that we calculate that's produced in the early universe. It was the first time that's been done, and all I can say is it makes a difference. Michael and James claim that it's actually felicitous, has some leverage on the missing satellite and too big to fail issues, although I think you can invalidate it if you find some more dwarf galaxies, and that may have happened recently. And there may be ideas for direct laboratory detection of these things, but really X-ray astronomy is our best bet to constrain these guys. And the reason for that is that tiny admixture of active and sterile allows these things to decay. And what happens is you'd have a sterile neutrino decay into an active neutrino and a photon. And if you think about how that works, if this stuff were the dark matter, it's essentially at rest, and that sterile neutrino then will turn into two relativistic particles. So the photon that comes off with an energy that's half the rest mass. Half the rest mass. That's an X-ray. And so we have X-ray telescopes, and you can look at this. And there's a lot of controversy right now about what these things, whether the X-ray observations rule these things out. There's a putative detection of a line that might be from sterile neutrino decay, and it might be from argon and potassium. So I'll just leave you with that.
All right, questions for George?
So will the process of outflow be much within the neutron decay time scale?
I'm sorry?
Will the process of outflow, the neutrino-driven outflows of compact objects be much faster than the neutron decay time scale? You say that you don't want the neutrons to turn into protons to feed the neutrinos, but can't the neutrons just decay into protons by themselves?
Yes, but that takes a long time. So free neutron decay, the lifetime is of order 10 minutes. So that's long compared to the time scale in which we're going to make this R process. Yeah. Not too worried about that one. It's the lepton capture reactions that will go much, much faster than that are the dangerous thing.
So going back to this Bullock calculation.
Yeah.
So how distorted was the sterile neutrino spectrum relative to a thermal spectrum?
Quite. They used the calculations. Let's just say that we went with the observation, which is suggesting that there's a 3.55 keV line. This is the. No, I know what you're asking.
I'm not interested in the details of that. What I'm interested in is, from what you said,
Yeah.
a sort of standard warm dark matter calculation would not work because usually you're just sensitive more or less to the energy density, and this one's saying that because there's a distortion in the sterile
That's right.
neutrino spectrum, that means they've got different velocities.
Yeah.
Which you could probably roughly take into account by doing some kind of...
Yeah, and I think in their calculation they're saying that the rough taking account of this actually is not quite right.
No, it wouldn't be quite right. It would be
Yeah.
probably pretty close.
Yeah.
Yeah, okay.
So, I mean, these things are usually labeled as warm dark matter, and they need not be.
Yeah, well, and so the question I have, are you saying you have a plot here?
Here it is. Can you see it? So that's a thermal spectrum.
Yes.
This dark thing is the actual spectrum.
Wait a minute.
This is a thermal active neutrino.
No, what's the...
This is.
okay, but that's...
Yeah, you can't read this very well at all.
No, anyway,
Yeah.
fine. But, most of that is just from the overall number density. And then they're colder.
Yeah.
Because the mass is, the freezing out is different, I guess.
Yes. Well, they're already frozen out from the
Let me
beginning.
take this a step further. Does this mean that you can't do warm dark matter calculations without having had a tightly coupled early universe calculation?
No, it just says that this isn't warm dark matter. It just says this isn't warm dark matter.
Well, what do you mean it's not?
So if you're going to kind of try to constrain sterile neutrino dark matter by claiming that it's warm dark matter, that's actually a mistake. That's the point.
Yeah, but it's all a relative issue about how big a deal it is or not.
Sure, sure. But these guys, I think, were the first to try to quantify, actually try to do the calculation and figure out what the actual spectrum looks like in terms of, leverage on small scale end of large scale structure. So, I don't know much more about it than that. Trying to find the actual spectrum they have. I don't think I have it.
Is there any hope for neutrino counterparts for neutron star LIGO detected?
Not a chance not a snowball's chance in hell. Okay, not unless the one is very nearby in the galaxy, which seems rather unlikely. So it's what I like to call the greatest injustice in the history of the universe. All the energy comes out in neutrinos, and very little actually in gravitational radiation. Don't judge this by the April event, merging black holes. All of that energy comes out in, whatever it was, some huge number of 3 solar masses worth of gravitational radiation. For neutron star mergers, most all of that is coming out of neutrinos. And so why is that? I mean, why do you have such small amounts of energy coming out in gravitational radiation? You can detect that out to 200 megaparsecs with advanced LIGO. And we'd have to have something within about 10 kiloparsecs or so to detect it, or at least tens of kiloparsecs to detect it in a neutrino detector. And the answer is coherence. So with gravitational radiation, you can get this whole 4 kilometer long laser interferometer arm moving coherently. That's the point. The de Broglie wavelength of these neutrinos is like 10 Fermis. So the best I can do is get a nucleus moving coherently. And that just doesn't make it. I'm sorry. When I can compare the length scale of a nucleus with 4 kilometers, it just doesn't cut it. So that's.
What could you learn about sterile neutrinos from a galactic supernova measurement?
What's that?
What could you learn about sterile neutrinos from a galactic supernova measurement?
Potentially a lot. We could certainly, if we have a good signal from a galactic supernova, which we probably will, given the existing neutrino detectors, if they're around and still funded when one goes off, then we would learn a lot about neutrino physics. We mostly learn about how neutrinos are emitted from these hot collapsing objects. But there are many interesting issues that sterile neutrinos can do. Certainly, if we're dumping energy at all into sterile neutrinos, that can show up. So I can show you that, for example, if we had this dark matter stuff, that could have an interesting effect. And here's one, for example. So here's rest mass of sterile neutrino. Here's some sine squared of mixing angle coupling, vacuum coupling. And everything, the parameters you see here in yellow would affect the infall physics of the collapse and basically affect the way in which energy is transported out of the collapse core. So if I look at these numbers, and I think I've got this on here, if I put on the 3.55 keV line detection, which would be a 7 keV neutrino, it falls right in a range that might do something interesting.
Precisely what is the mechanism in the core collapse context that you did?
Okay, so what could happen is that an active neutrino, as I showed you, is rattling around in the core, and then it turns into a sterile neutrino, and it zips out at the speed of light. Okay, so that could happen, in which case you're removing energy from the core. And one thing we could get from a really good time series signal, neutrino signal, is kind of the time scale in which the core cools. Cool is a loaded term in astrophysics, because when things cool off in astrophysics, they actually heat up. That's why white dwarfs are white, right? So the neutrino radiation becomes harder as the thing, sinks deeper in the potential well. So We don't know much of anything from 87A. There were 19 events, if we don't count the Russian events. What's that? Seconds, but it's not enough to say anything definitive in a physics sense.
This is all what you're referring to, though, in the Bartlett's context. It's all involved with wave and state issues, too, right?
Absolutely. So I'd have to back out. I'd have to know something about the equation of state to make a hard physics constraint on some aspects of neutrino physics, including this one. So one thing that can happen is this active neutrino is rattling around. It hits some resonance region, turns into a sterile neutrino, and then turns back into an active neutrino before it gets to the neutrino sphere. What have you done then? You've kind of renormalized downward the transport time to get active neutrino energy out. You get the neutrino luminosities up from the neutrino sphere, which actually has a lot of interesting consequences.
Can you raise the temperatures of the neutrino spheres?
Effectively, that's what I'm saying. If the luminosities are going something like 4 powers of the temperature, for example, then yeah, you're essentially doing that. So we don't know. This is total speculation.
All right, maybe that's